Okay guys, in this video we are going to go through several examples of reaction mechanisms. We'll start with gas phase unimolecular reactions, and so this would be things like decomposition of a gas phase molecule or an isomerization reaction. These often exhibit first order kinetics, and they typically involve a high activation energy, at least compared to the thermal energy in the system. And the way that the gas molecules obtain that energy is through collisions. And so this Lindman mechanism, as we will call it, involves two primary chemical equations. The first one is reversible in the sense that you have two gas molecules come together, and the collision excites one of the gas molecules, and the other one just kind of recoils. That excited molecule can either collide with another molecule and go back to the unexcited reactants, so this would be the excitation step and then the de-excitation, or the excited molecule can then fall apart into the products with a separate rate constant. Okay, so we have these two primary steps, or three primary steps, depending on how you want to count them. Here's just a diagram of that process. These two molecules collide, one recoils, one becomes excited. Either a collision can occur which will de-excite the molecules, or the excited molecule can then go on to form whatever products that we have. And so we're being asked to use the steady state approximation to derive the rate law for this so-called Lindman mechanism. And so we're going to focus on the formation of the product, and we need that second step. We need to know the concentration of the excited reactant, which we'll treat as an intermediate. So writing out the time derivative for that, we see that the first step produces it, and it's a second order, or it's a bimolecular type 1 process. The de-excitation step consumes some of that excited molecule, and just note that I've got a typo here. I should have this rate constant should be distinct from that one. They are not the same, and that's true on this slide as well. That should be Ka prime. A star A. And then the last step also consumes some of the excited molecule. So we're going to use the steady state approximation here, set that approximately equal to 0, and solve for the intermediate concentration. And you wind up with, let's see, Kb plus Ka prime times A. Okay, and then that goes into the expression here for the rate of production of the product. So we'll have Ka, Kb, it'll be A squared over Kb plus Ka prime A, and so it's a complex mechanism, and so we have a complex rate law. Let's examine two different conditions. Let's do first high pressure. So high pressure means that the concentration of A times Ka prime relative to Kb is going to be much, much larger. And in terms of the mechanism, what that means is if there's a lot of monomer floating around, high pressure, that means that the excited molecule is going to very frequently encounter a collision and then become de-excited. Okay, so what it means is there'll be less time available for the excited molecule to form the products. If it's constantly colliding with other A molecules, then the de-excitation pathway step is going to be favored over the reaction pathway. So mathematically that translates to this expression, and what you wind up with is that dP over dt, you can neglect kb relative to ka prime times a. And so you wind up with ka kb over ka prime a squared, and you are going to observe second order kinetics. And then your observed rate constant will be this combination of rate constants here. However, for low pressure, the opposite is true. If there's not a whole lot of gas molecules running around, then the de-excitation step will not be as favorable, and the molecule is going to have more time to react to form the products. And so in that case, you can, it's the opposite mathematically. Ka prime a will be much, much smaller than kb. And so now you can neglect that term relative to this one, and you wind up with ka a squared. Sorry. The square should be on the outside. And of course I've messed that up. It should be Ka, Kb, Ka prime, A. This should be A squared, like so. And then what I've done is I have failed to cancel that. And so this should be Ka Kb over Ka prime times A. Sorry, for high pressure conditions, you would observe first order kinetics, right? So if you neglect this term, the A squared is going to cancel one, the A down here is going to cancel one of the A's in the A squared, and so you'll be left with first order kinetics and this combination of rate constants. However, if you neglect that term, you're going to observe, you're going to get Ka times A squared, you're going to observe second order kinetics. And so the point that I wanted to highlight here in this Lindman mechanism is that the different experimental conditions lead to different observed kinetics. So, under high pressure conditions, you're going to observe first order kinetics, but under low pressure conditions, you're going to observe second order kinetics. And so that shows you the richness of complex mechanisms in terms of the experiments that you can do. This slide is really just a summary of everything that we've done in the derivation, with all of the typos that I made fixed. Here in this problem, there's one more equation that needs to be arrived at. You're being asked, you're given some information about the Lindman mechanism. So you're given the observed rate constant for one concentration of the reactant, and you're given the rate constant at another concentration of the reactant, and you're being asked to calculate the value of the Ka. Here is the effective rate constant from the mechanism. So if I go back, you can see that if you take all of that part and call that the effective rate constant, or let's see, well, they've separated this and combined one of the concentrations here. So they've introduced this effective rate constant. What you can do, if you play around with this equation, so this is effectively what you would observe under the assumption of unimolecular kinetics. You can take 1 over this effective constant, and it's going to give you, we'll just work through it, Kb plus Ka prime times A over Ka Kb times A. Here what we can do is distribute this, and so we'll get 1 over Ka times A plus, this is going to give us Ka prime Ka Kb. And now if you take 1 over K2 minus 1 over K1, you're going to wind up with 1 over Ka A1 plus Ka prime Ka Kb minus 1 over Ka A2 minus Ka prime over Ka Kb. These two terms cancel out, and so now by combining the effective rate constants, looks like I did it backwards, K2 minus K1, so it should be 2 and then 1. You'll wind up with I guess we could simplify it even more. 1 over Ka and so now between these numbers and those numbers which are given, you can find Ka. I'll just leave that to you as an exercise. It's not that critical of a problem. So I'm just going to move on. And we're going to talk about the next types of mechanisms. So that was the Lindemann mechanism for unimolecular gas phase reactions. And that would include things like decomposition and isomerization reactions. Next, we're going to talk about the kinetics of polymerization. So recall that polymers consist of identical monomers, and there are two. I mean, there's all sorts of polymers and polymer kinetics, but then there's two big categories that I'll talk about. One is called stepwise polymerization. This is where any two monomers in your reaction mixture can link up at any time. And the main thing to remember, the key takeaway, is that the average molar mass of the polymer grows linearly with time. So the longer you let the reaction go, the bigger your polymers. Here's a diagram illustrating the stepwise polymerization. So here, these green spheres at early time represent your monomer, and then, any two can link up to form the next generation of polymers. And so these guys are going to react. This one's going to react with that one. Okay, so that formed these two. Now in the next step, okay, these two are going to link up, and that's going to link up, and this one's going to link up with that one, and so on. So in the stepwise polymerization, the growth can start between any pair of monomers that you have. The other classification of polymerization that I'll talk about is chain polymerization. Here, this is where the polymer chains grow from the ends, and what is found is that, and this is the main takeaway, in chain polymerization, the average molar mass does not increase with time. So for stepwise polymerization, chain length increases with time. For chain polymerization, it does not increase with time. Here's the picture for chain polymerization. So you've got these chains. The polymerization occurs at the ends. And then you've got now these new chains, and then they polymerize at the ends. And then these guys again would react at the ends to form increasing length polymers. Let's start with the stepwise polymerization. We're going to look at condensation. So this is a type of stepwise polymerization. So condensation is often involved where we've got two polyesters that react, and the reason it's called condensation is because water is eliminated from the reaction. So these two hydroxy acids molecules, they will combine, eliminating water, and then the chains get longer and longer. So what we're going to do, a little bit of notation just to make things easier so we don't have to write this all the time. We'll let the symbol A represent the concentration of the carboxylic acid groups that are present, and then we'll let OH represent the concentration of OH groups that are present in the system. And so for this reaction, okay, the rate at which the concentration of the carboxylic acid changes will be minus, because it's decreasing, a rate constant times the concentration of the OH groups times the concentration of the acid groups. And due to the stoichiometry of the molecule, okay, for every acid group there's an OH group, and so we can just replace OH with A, and that's going to give us this second order kinetics expression. And here's the integrated rate law for that second order kinetics. Okay, so this is the concentration of the acid group as a function of time, and it's going to decrease with time. Now, what we're constructing here, this number will be the fraction of the acid groups that have condensed. So this is the amount of acid that you're starting with, minus the acid that you have at any given time t, divided by the amount that you started with. So this represents the fraction of acid that has reacted, if that makes sense. And you can take the second order equation that we have from the kinetics and just substitute that in, and it will give you this equation right here. Now, the quantity that we're interested in is called the degree of polymerization, and it represents the average number of monomers per polymer. And so that's constructed by taking A0 divided by A. It can also be written in terms of this fraction of acid condensed, but you can also calculate this directly from the second order integrated rate law. And it gives you an expression that increases with time. And so that's the main result here. The number of monomers, average number of monomers per polymer, increases with time. So consequently, the average molar mass increases with time. This problem here, it's not particularly important. They simply give you the information you need in order to calculate these two quantities. So given a rate constant, given an initial concentration of monomer, calculate P, the fraction of condensed monomer, and then calculate the degree of polymerization at a particular time. And what they're doing on the next slide is kind of interesting. They're plotting N as a function of P. So the average chain length is a function of the fraction condensed. And what this shows you that in order to get to pretty long chain length, you have to condense quite a large amount of the polymer. So take-home lesson, the average chain length for stepwise polymerization depends upon T, it increases with temperature. The longer you let your condensation reaction go, the longer your polymer chains. Let's talk about the other mechanism that I wanted to mention, the radical chain polymerization. So this involves radical intermediates. And so you typically have some initiator, so some agent. It can either be a chemical or it can be a photosensitive compound that you'll initiate using a bright light, a bright ultraviolet light. Let's just assume it's a chemical compound at this point. But anyway, that initiator forms radicals, and those radicals will then react with a monomer to form a monomer radical. And the 1 here indicates that this is a chain of unit 1 length in terms of the monomer. That monomer radical can then go on to react with another monomer to create a monomer chain that's 1 unit longer. And then this guy can then go on to react with another monomer to get an even longer chain, and so on. And so that's what we mean by it grows at the ends. The chain reactions can be terminated, okay? And so you could have 2 monomers come together, or not 2 monomers, 2 polymers come together to form an extra big polymer, and then now this thing is no longer a radical, so it won't react anymore. Or you can have all sorts of other termination reactions occurring. We're going to focus on this one right here. We won't worry about the rest of it. Okay, the rates of these reactions. So treating this as an elementary step, the rate of initiation is some Ki times the concentration of the initiator. We are going to effectively treat every chain as being equivalent. So we're just simply going to lump all values of little n here into the same concentration and not worry about the distinction between n and n minus 1. So the rate of propagation is going to be proportional to the concentration of the monomer that we have, which will decrease with time, times the concentration of the chain radicals of any size. Kp is the propagation rate constant, and then we're just going to focus on this type of termination where we've got the termination rate constant, and this refers to any chain length radical. And because the two chains come together, it's a second order step. Okay, so we've got these three rates work. And what we're going to focus on first here is the, well, let me start here. What we're really interested in is the rate of polymerization. Okay, and so we looked at that on the last page. And so we need to know, what is this guy? Okay, this is the one that's kind of difficult to deal with. And so let's look at the rate at which the radicals are produced. Okay, and so the radicals are produced in the initiation step. Okay, so for each initiation, there are two radicals produced, right? And then those go on to produce two chain radicals. Okay, and so that's why we have this 2 times nu I, and then the factor F refers to the fraction of radicals that initiate a chain, meaning your initiator forms radicals. Perhaps not every radical will go on to form a chain. Some fraction of the radicals formed will. So that's what that little fudge factor is there for. Okay, so that adds to the concentration of the chain radicals. And then how do we lose chain radicals? Well, the propagation step doesn't consume radicals. It just makes them a little bit longer. So this propagation has no impact on what we're calling this kind of averaged chain radical. The termination step will, however, and we see that, you know, in the termination step we lose 2 chains for every termination event. So we're going to take 2 times the rate of this to measure the impact on the concentration of the chain radical. So each termination step will effectively consume 2 of our radical chains. And then what we'll do is we'll make the steady state approximation. So we'll set this equal to 0. So taking the expressions from the previous slide for these 2 rates, making the steady state approximation and solving for the chain length, we get this result here, where the steady state approximation for the radical chain is expressed here in terms of these rate constants, and it's the initiator concentration to the square root power. So we can take this guy, substitute it into our expression for the rate of polymerization, and we get that the rate of polymerization is equal to, or is proportional to, the concentration of the monomer times the concentration of the initiator to the square root. What we're really interested in is the chain length, okay, and that's the number of monomers consumed divided by the number of radicals produced. Okay, and so we can calculate that guy. It's going to be the ratio of these 2 rates, and when you substitute in the expressions that we've been working with, so this expression here that we derived for the rate of polymerization and the rate of initiation, which we can play around with, but anyway, we get to this final result here where we see that the average chain length, which is equal to 2 times this lambda factor that we derived, does not depend upon time. It does not increase with time. It's related to the monomer concentration, and then it depends upon the amount of initiator. So it doesn't. So once you've got your chain reaction going, the length of the polymers will not depend upon how long you let it go. They're going to depend upon on the concentration of initiator that you started with. So you use a larger concentration of initiator, it's going to give you a larger average molar mass. Next, we'll turn to some mechanisms involving catalysis. So as we've discussed previously, catalysts are species that increase the rate of a reaction and are not consumed in the reaction itself. So in a sense, catalysts are recycled and can be used over and over again until they break. The way they work is they provide an alternate mechanism for the reaction, which I think always involves a lower activation energy for the reaction to proceed. So a different mechanism is provided with lower activation energies. One thing to note, and I mentioned it previously, is that the catalyst will not affect the equilibrium concentration of your product. It will only get you to equilibrium faster. Now that may be a big cost savings, and so that could be a very good thing, but you can't do something like take a 10% yield reaction and turn it into a 90% yield reaction with the catalyst. There's two main types, homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis is when the catalyst has the same phase as the reaction mixture. So in this case, we're considering a redox reaction in aqueous solution, and our catalyst is an aqueous species. And so here is the uncatalyzed reaction. So cerium-4 being reduced to cerium-3 and thallium being oxidized to thallium-3 is very slow on its own. However, if you sprinkle in some manganese compound in there, what will happen is a different reaction mechanism will be provided, where the slow step of the new mechanism is still faster than the very slow step of the original uncatalyzed mechanism, and so overall you're going to get a net increase in the rate. And you can imagine that the overall rate of the process has two parts. We've got this very slow part for the uncatalyzed reaction plus a term for the catalyzed one. This is going to be much larger than that one, and so you can typically neglect this one relative to this one, but nevertheless they will compete with one another in principle, and it just depends upon how big that rate constant is compared to K. Heterogeneous catalysis, which is I think the industrially more important one, is where the catalyst has a different phase than the reaction mixture. So very common would be a solid metallic catalyst of some sort in a gaseous reaction. So this would be the case for something like a catalytic converter in our automobiles and other types of engines. Or you could also have heterogeneous catalysis involving a liquid and a solid. I know that many, well, I don't know how many there are, but I know that certain reactions in the atmosphere take place on the surface of clouds and things like that, where the surface of the cloud basically acts like a heterogeneous catalyst, and so it's proportional to surface area and things like that. In the example that we're looking at here, we're talking about hydrogen and nitrogen. Okay, so typically, you can mix nitrogen and hydrogen and leave them alone and they'll never react. However, if you do this in the presence of iron, you see that the activation energy for the catalyzed reaction is quite a bit lower than the activation energy for the uncatalyzed reaction. So hydrogen and nitrogen in the absence of iron is kinetically stable, even though thermodynamically it's favorable to form ammonia. However, add some iron catalyst to it, you're going to lower the activation energy, and that's going to greatly increase the rate of the reaction. Okay, so that's an example of heterogeneous catalysis. We've already seen this picture. The way it works, the activation energy is dropped by the new catalyzed pathway. The point to, you don't want to read too much into it. Like I said before, this is going to increase both the forward rate and the reverse rate by the same amount. And so the equilibrium constant, which depends upon the energy difference between the reactants and products, will not be changed. So you can speed up how quickly you get to equilibrium, but you will not alter the equilibrium distribution of reactants and products. Well, in the last few slides, I wanted to say a quick word or two about enzyme-catalyzed reactions. So this would be catalysis in biochemical systems, molecular systems, biological systems. Enzymes are Mother Nature's catalyst, okay, and they are extremely selective. So that means they do a specific reaction, and they're very potent. Okay, so they make a big difference. A lot of diseases out there are due to enzyme deficiencies. Someone's body doesn't produce a particular type of enzyme, and that can lead to lifelong chronic problems in some cases. Enzymes are typically proteins, as far as I know, and what they do is they have active sites on them that bind a particular molecular substrate, which enables a reaction to take place, and then the products are then released. There's two primary models that I know about. I'm sure there's more. One of them is called the lock and key model, where the enzyme is perfectly designed, so to speak, for the substrate. That is, that only the substrate will fit in that active site on the enzyme. That's illustrated here. And then the other one, which some of the resources I read indicate is more common, is that the so-called induced fit, that the enzyme has a general active site, which when the substrate docks on it, then a conformational change occurs inside that protein, which then makes it fit, basically locked into place. This substrate enzyme complex then will undergo the reaction, and then that will release the products. Here are the primary observations for enzyme catalysis. The initial rate of product formation is proportional to the total concentration of enzyme. Okay, so early on in the reaction, the rate of reaction is proportional to the enzyme concentration. When the concentration of the substrate is very small, the rate of the reaction appears to be proportional to the substrate concentration. However, when the substrate concentration is very large, the rate of the reaction is independent of the substrate concentration and appears to have a maximum rate, regardless of what the substrate concentration is, as long as it's large. And so these are the observations that need to be explained. And here is just a picture of what we mean, that when the substrate concentration is small, the rate of the reaction depends upon the substrate concentration. When the substrate concentration is very large, you see that the rate of the reaction sort of turns over and reaches this maximum velocity. As you probably already know very well, better than I, it's the Michaelis-Menten mechanism that explains this. What is that? Well, we have a pre-equilibrium being set up here between the enzyme and the substrate and the enzyme-substrate complex. Okay, there's a forward rate constant and a reverse rate constant. That enzyme-substrate complex can then react to form the product, and the enzyme is recycled in the process. So we are interested in the formation of the product, so the rate of the reaction will be this Kb times the concentration of the enzyme-substrate complex. We will use the steady state approximation for that. So setting up the time derivative for the enzyme-substrate complex, we see that the forward term here, Ka times the concentration of the enzyme times the concentration of the substrate, that's the rate for this first step. We've also got the backward step and then the product step, and that gives us this term here. Following the steady state approximation and setting that equal to 0 allows us to derive an expression for the enzyme-substrate complex, where this Km is the Michaelis-Menten constant. It's defined as Ka prime plus Kb over Ka. Now we'll do a little trick here, noting that the initial enzyme concentration for all time will be equal to the amount of enzyme that we have floating around plus whatever enzyme is occupied with the substrate in the substrate complex. And that's because the enzyme is ultimately recycled, so the concentration of enzyme is never lost. It never turns into something else. It's either floating around on its own or it's tied up in the substrate with the substrate as a complex. Furthermore, if we have sufficient substrate that the concentration of that substrate is effectively constant, doesn't change with time, then we can substitute into this expression and simplify things a bit. It leads us to this expression here, which we can then substitute into the expression for the rate. Okay? And so what we want to do is analyze the rate in terms of these quantities. So what do we see here? Well, we see that the rate depends upon the concentration of the enzyme. So the initial concentration of the enzyme. So early on in the reaction, when this, before any reaction has occurred, we can see that indeed the rate is going to depend upon the concentration of the enzyme that we have. And that was one of our observations. I believe it was the first one that we made. Yeah. Depends on E0. Let's look at the substrate now. What happens when the substrate concentration is rather small? Okay, so if this is a small number, that means 1 km over that small number is going to be big, much larger than 1. And so that effectively means that for the case where the substrate concentration is very small, we can neglect that 1 and we'll effectively have Km over S0, Kb E0 over Km times the substrate concentration. So here what we see, when S0 is small, the rate will depend upon the substrate concentration. When it's very small. However, when it's very large, then that means that we would neglect this term, right? If this number is very large, that means that 1 over that number is close to 0. So we would neglect the 1. And in that case, we would get that the rate would be Kb E0, which would effectively be this rate max. Okay, so the Michaelis-Menten mechanism leads to a rate law that satisfies all 3 of these observations. And what did I have last? Okay, so the last thing, I'm not an expert on this, but anyway, this is the Lineweaver-Burke plot. If you take the natural log of this equation, not the natural log, sorry, 1 over this rate, it flips this guy around, and so you get an expression that looks like this. If you plot 1 over the rate as a function of 1 over the substrate concentration, you're going to get a linear equation where this is your slope and this is your intercept, and between the slope and the intercept you can determine both Km and the maximum rate, which should in turn allow you to calculate some of the rate constants, I would suspect, perhaps. In any case, here's an example of that. You plot 1 over the rate versus 1 over the substrate concentration. The slope is related to Km over V max, and then the intercept is related to 1 over the maximum rate. And so between, when you do your linear fit, you would get, you could get these numbers. Essentially, that's what this problem has done. I didn't even write down the data, but here's basically the data that you were supposed to plot. And so by determining the slope and the intercept, you would get those quantities. So with that, I'm going to go ahead and stop this video right here.